But as you know, we generally, for this workshop, we kind of randomize the topics of the talks, but in a master stroke of scheduling, we do actually have two talks that are closely related back to that. So Ivona is going to tell us about complementary results to what we've just heard from, yeah.
Exactly. Thank you, Alistair, and thank you for inviting me to come and speak here. So what I'm going to talk about is the complement to Jan's talk, the inapproximability of the independent set polynomial in the complex plane. Funnily enough, my introduction is going to be very closely aligned to Jan's. I'm going to run through it quite quickly, but we might have some people in the audience who didn't come for his talk, so I'll go through it anyway. So we are given a graph G, and an independent set is a set of vertices where we have no edges between them. So this is an example of an independent set of size 3, and it is a very well-known NP-hard problem to find a largest independent set. So what people have looked at as a complementary way of looking at the problem is, what if we don't try to go for the optimization problem? What if we don't try to find the largest one, but what if you look at all of them? Okay, finding a small independent set, namely the empty one when we don't have any vertices, is an easy problem. But the problem is that all of independent sets, there can be up to 2 to the n of them, so exponentially many, which from computer science perspective is a little bit of a problem because we don't have that time to enumerate all our independent sets. Well, and then there is yet another version of the problem, and that is a weighted counting of all independent sets. So now we have a certain parameter, this lambda, that we will call activity. And what it does, it kind of gives us a way of fine-tuning whether we want to go for small independent sets or large independent sets. So if lambda is bigger than 1, we are going to give, for any lambda, we are going to give the weight of lambda to the number of vertices in my independent set. That's going to be the weight for this independent set. And so if lambda is bigger than 1, we're kind of giving larger weight to the large independent sets. If it's smaller than 1, we're giving weight to the smaller ones. And this brings us to the independent set polynomial. So the independent set polynomial is simply sum of all of these weights. And I worked it out, and I think this is the independent set polynomial for my little toy graph that I'm showing you. And as Jan mentioned, this is related to the partition function of the hardcore model of gas from statistical physics. I'm not going to repeat what the hardcore model is, but it's a studied quantity when we have positive lambda, positive real lambda, and Jan also mentioned that physicists are actually even looking at negative values. So what is our problem statement? Given a graph, lambda, we want to compute the value of the independent set polynomial for this specific lambda. Okay? And that's what's called the partition function as well, though I will try to steer away from that because I think it's mostly used for lambdas being from the real world. Okay. So there are some exact computation results, namely for some special graph classes like bounded tree with graphs, we can compute this value exactly. It's not surprising, it's useful in some scenarios, but it's not very surprising. However, dating back to 1979, to the original introduction of the so-called Sharpie class of counting problems, Valiant showed that it's actually Sharpie hard to evaluate the independent set polynomial for lambda equal to 1, which corresponds to counting all independent sets. And so this, from computational perspective, tells us that it seems very unlikely that we will be able to design a polynomial time algorithm that computes the number of independent sets. No way. And then Bulato-Grohe and Kai Chen and Lu extended this Sharpie hardness result for any complex lambda, trying to get the full classification. So this is exact computation when we want to compute the value of the independent set polynomial at lambda exactly. So we have hardness, seems unlikely. So let's move to approximation. So approximation, and we are going to restrict ourselves to graphs with bounded degree. We're going to use capital delta as the bound on our maximum degree. we know that exact computation was difficult for the bound 3, even for 3 regular graphs. When my graph had, every vertex had 3 neighbors, it was already hard to compute the independent set polynomial exactly. So this brings us to this notion of FP-TAS, fully polynomial time approximation scheme. And what it is that we get, I am phrasing it here for the specific problem of computing the independent set polynomial. So I'm given my input, which in my case is the graph G and lambda, but I also have a kind of error, epsilon. And what I want to compute a value that is within 1 plus minus epsilon factor of the independent set polynomial evaluated at lambda. But I want to be able to compute this value in polynomial time, just polynomial in the size of the input. Okay? And so now this picture that is coming here is going to look eerily similar to Jan's. These are exactly the same results that he mentioned. So we have a critical threshold, and Rohrweitz back in 2006 showed that we have an FP-TAS in the regime for lambda up to this critical threshold that depends on the maximum degree of my graph. A beautiful result based on correlation decay, which was then followed by a series of work starting with a very nice result by Alan Sly and then continuing with 2 other follow-up works that showed that it is NP-hard to approximate the independent set polynomial beyond this critical threshold. By the way, I am staying within the realm of deterministic algorithms. There are also some randomized algorithms over here, but I'm just not going to mention them now. And then Andreas Galanis, Leslie Goldberg, and Daniel Stefankovic. Oh, I should have mentioned, I wanted to highlight my co-authors. So this is joint work with Andreas Galanis of Oxford, Leslie Goldberg, who is sitting right here, also of Oxford, and Daniel Stefankovic. And so the 3 of them did prove NP hardness of approximation up to this shear threshold quantity, which depends again on the maximum degree in my graph. It's really minus this quantity. And this is a very, very nice result. And that brings us to a little detour of the Lovász local lemma. I'm actually not going to go through this because Jan did such a wonderful job talking about the Lovász local lemma. So the bottom line, okay, this is a little bit much cruder description of Jan's, but the point is that Lovász local lemma is connected to computation of independent set polynomials, even for negative and possibly even for complex lambdas through the work of Scott and Sokal and Shear. Okay, so for the motivation, we want to compute independent set polynomial values for lambdas, even in the negative regime, but also for complex values. And so that brings us to Jan's beautiful talk, where he was talking about an FP-TAS within this little circle around that extends all the way to the shear threshold bound. And that's the radius of the circle. And then we have also an FP-TAS using, what was it? Barvinok philosophy. We have very nice results by Patel and Gustrecht over here, who also can handle exactly the same circle. Now, Peters and Gustrecht have this small rectangle around the positive real line all the way to the threshold, critical threshold. And after that, they also, in the very same paper, identified this cardioid region, which is a region where certain recurrences converge, certain univariate recurrences converge. I'll talk a little bit about that in a second. But somehow, the original intuition was that maybe we could have polynomial time approximation algorithms for lambdas drawn from this cardioid shape and not outside. Okay? Now, my picture is stuck in 2018. We saw an updated picture. So there is one other thing that is happening in 2018. Okay, this is a very, very crude picture because I am using PowerPoint, and I apologize to Benj and Chikwari. This is really not what it should look like. Look at Jan's slides. or their paper. It's supposed to kind of be like this. But they identified a region where the independent set polynomial doesn't have any zeros. And then from that, it follows that there's an f-betas in that region. So the part that is missing here are the little points by Buys. Am I pronouncing it right?
Buys.
Okay, thank you. Those, the little points over here, little lambdas, for which the independent set polynomial has zeros, and the lambda is within the cardioid region, and also these kind of green little nice region that Jan and Piyush Srivastava did just very recently, as of last week ago. Okay, so this is the picture, and now what do? Well, we do the outside. So the outside is, we are going to show that it is sharply hard to approximate our independent set polynomial outside of this cardioid region. Okay? And in particular, we are going to show that it's sharply hard to approximate either its norm or its angle. I'm going to be focusing on the norm. It's a very similar approach. Okay, so now, what's going on? So what we want, let me go back. So we are going to draw lambda anywhere outside of our cardioid, and we want to evaluate, and we are also given a graph, and we want to evaluate, meaning approximate the norm of the independent set polynomial for this lambda. Okay, that's the setup. Well, except what we are going to do, let's for starters actually extend ourselves to the multivariate setting. What does that mean? Before, every vertex was equal. Every vertex, if it was in the independent set, it had contribution lambda. Okay? Now, let's give a different activity to every vertex, and so we are going to do exactly the same thing, but now for a given independent set, we are going to take product of the lambda. And we claim that it is sharply hard to approximate the norm of the multivariate independent set polynomial. And how does that work? And so, what we are going to do, we are going to pretend that we can approximate this norm. And then from that, we are going to conclude that we would be able to solve the problem of computing the number of independent sets in a given graph exactly, which we know is a hard problem, which means that our problem has to be hard as well. Okay? So here is a picture. This is the graph H that we are given, for which we want to compute the number of independent sets. Okay? We are going to transform it into a graph G by adding a new vertex, connecting it to everybody else, and setting the activity at this vertex to, this is a minus, to minus some value m. All of the other vertices are going to have activity 1. Okay? So now, what happens if we try to compute the multivariate independent set polynomial for this graph? Where we are going to approximate this multivariate independent set polynomial, but what is it? Well, either this new vertex is in the independent set, in which case nobody else can be in the set, and therefore the weight of that set is minus m, or the vertex is not there, in which case we have exactly the original independent sets in our original graph. Okay? So we are really estimating the absolute value of these two numbers. So what we are going to go for, we are going to try to find m such that this quantity is equal to 0, which will let me output exactly the number of independent sets in the original graph. Okay? Now, I don't know which m to start with. I know the number of independent sets can be anywhere between 1 and 2 to the n. So it sounds like some kind of a binary search. Trying, but we have to be just a little bit more careful. So here are several points that we need to address. The first thing is the binary search on m. I just have a little picture here. So m ranges anywhere between 2 to the n and 0, and this quantity is an absolute value, so we have to be a little bit more careful with binary search. We cannot just look in the middle because we don't know whether we can eliminate the left and right. We have to approximate our independent set polynomial at several values, but a constant number, and based on that we can eliminate some. part of the range of n. Okay, so that's a small technicality. Now, the next thing to notice is, I didn't really highlight it. Let me go back to the theorem. Where is the theorem? Here. It is sharply hard to approximate the independent set polynomial. So I'm assuming that I fixed my maximum degree. Okay, so I have a fixed delta because my cardioid region depends on the maximum degree. Okay, but what did I do with this reduction? I suddenly introduced a vertex that has a very large degree. So I need to then, well, deal with it. And so that brings us to this degree reducing gadget. So what, this one. So we can come up with a graph that has two vertices of degree 1 that has the effect of when u and v are of opposite membership in an independent set. So u is in an independent set and v is not, or vice versa. The independent set polynomial restricted to such independent sets is going to evaluate to 0. So this gadget essentially has the effect of forcing u and v to be either both in or both out. So it's doing an equality. Okay? I'm not going to go into the details here. This is just a kind of remark on the side that it is not difficult to deal with the large degree vertex that we introduced. Okay? And it turns out that this gadget for us is just going to be a simple path where we carefully select the activities, path of length something like 5, where we carefully select the activities at these vertices just so that the contribution of u and v evens out to 0 if u is in and v is out, and vice versa. Okay? And so then when we have a graph of a larger degree, we can just split the vertex of a larger degree into multiple vertices, connect them with a gadget that enforces that these two endpoints have to be either both in or both out, and we've reduced the degree. Okay? Likewise, we can do the same thing to convert our graph into a bipartite graph. There is a bipartiteness gadget, again, just a path. So the only thing that we need to really worry about is that here we extended ourselves to the multivariate setting where we're allowing activities to be, well, 1 or minus m, or within this gadget there are a couple of other values. But what we really have is just lambda. We're proving that it's hard to evaluate the independent set polynomial for one specific complex valued lambda outside of the cardioid. So what we need to do, we need to somehow take our lambda and convert it to simulate other activities. So that's the setup that we are at right now. Okay, and so...
Why is bipartiteness relevant?
Say it again?
What was the point about bipartiteness?
Oh, it was just a stronger theorem that is actually sharply hard to compute to approximate the independent set polynomial even for bipartite graphs of bounded degrees. Okay, so now this is the setup. We needed different activities, but we are given only lambda. So we're going to play with our lambda, and somehow we're going to modify this graph so that it behaves as if it had the activities that I want, namely 1 and minus m. Okay? And so what does that mean? That means that we're going to do another gadgeteering. We're going to attach a gadget to every vertex, and it's going to be these blue thingies. And each of these gadgets is going to be responsible for having the effect of the vertex that it's attaching to having the desired activity. Okay? And it turns out that what we want for the gadget is, if we have a target activity lambda prime, so let's say minus m, okay? So once we attach these gadgets, all of these gadgets will have only lambdas in them. And these minus m's and 1's will not be there anymore. The gadgets will be acting as if it was of activity minus m or 1. So we take our target activity lambda prime, And we're going to create a graph gadget where we have one special vertex, V, the vertex that we are going to use to attach to. And then that has degree 1. Because we are going to, by attaching the gadget, we are going to increase the degree. So we don't want to have very large degree at this vertex. All of the other vertices here are going to have bounded degree by our delta, the bound that we have on the degree. And we will want the contribution of the independent set polynomial when this vertex is in the set. I'm using this notation. G, B equal to 1, B equal to 1 means that I'm looking only at independent sets where V is in. So the contribution of those independent sets over the contribution of the independent sets when V is not in, I want this ratio to be equal to, roughly, ideally, equal to lambda prime. In reality, it's going to be very close to lambda prime. Okay? Now, the question is why? Well, I just took the definition from the bottom of the slide up here. So what is the effect of attaching G to a vertex V? Well, if I have my original graph H, and then I do the attachment, and I thus create a new graph H prime, let's do a very quick calculation. So what is the independent set polynomial for H prime? Now, everybody has activity only lambda. So the V vertex is either in an independent set or out. If it is in, it has to be in the independent set for both H and G. If it is out, it has to be out of the independent set for both H and G. And so now when we just do a quick manipulation, namely when we divide both sides by the quantity when we don't have V in, the sets when V is not present, and we just divide it, nothing more. And then we look at what we get. Well, what we get is the contribution of the independent set polynomial only in the graph H, plus the contribution of the independent set polynomial only in the graph H when V is equal to 1. This was V is not in an independent set. This was V in an independent set. And then we have this ratio, which is really just our lambda prime. So the point being is that this gadget is what we are looking for, because that has the effect of simulating lambda prime activity at the vertex V. So now we moved ourselves, and what we are going to do, we are going to create this gadget. Now, what we also need to be a little bit mindful about, but it's a minor technicality, is that the target independent set polynomial, the one where we are pretending that we have lambda prime, is like the independent set polynomial when we attach the graph, but there is this devising factor, so we need to be able to compute it so that then we can adjust the quantity. So it's a small minor technicality, we just need to be able to compute this quantity, that's all I'm saying. Okay? Okay, so how are we going to create this gadget? So what do we want? We want a gadget where the ratio of the contribution of the independent set polynomial when my vertex V is in a set over not in a set equals to some desired target activity lambda prime. Okay? And well, the simplest possible graph we could try is a tree. So let's try that. Let's try to use a tree to construct our gadget. And so the advantage of using a tree to constructing this gadget is that we can compute these quantities easily. So the issue from the previous slide is not a problem, because a tree, we have a nice recurrence and we can just compute this. And we can construct the tree recursively. And so how would that work? Well, if we already have some trees that we constructed, and these trees implement different activities. So let's say this is activity lambda prime for tree T1, lambda prime for tree T2, and so on and so forth. What can we do? Well, we have all of these extra vertices that we can just merge. So if we just merge them and create one extra vertex at the top, what is the new activity? Well, this is a small computation. I'm going to use d to be the degree minus 1. So I'm going to be merging degree minus 1 trees so that I have still one extra degree left for my vertex at top. And so what I get is the following. We can just exactly the same type of computation that we had before. We can look at the contribution to the independent set polynomial when this new vertex v is in an independent set or if it's out. So if the new vertex is in, what is the contribution? Means that it is getting a factor of lambda, and then it means that all of these neighbors have to be out, so we are just taking a product of the out options for the smaller trees. Likewise, we can do the same type of computation for v equal to 0, and I'm not going to go through all the details, but it's not a difficult type of computation. But what it gives us a certain type of recurrence where we compute the new activity using the old activities. And, well, let's reparameterize so that the recurrence looks beautiful, or more beautiful. So we're going to divide the target activity by lambda, and then we are going to get this recurrence. So this is going to be the recurrence that we are going to be working with today. Okay? Now, looking back, what do we get out of this recurrence? Well, what we kind of want, this recurrence is we can compute these quantities by building trees. And so, if we start with some basic quantity, something that we can easily get by just having, let's say, one vertex, and then we are going to keep merging these trees and using these recurrences, we ultimately want to get lambda prime if we get okay, the only thing I'm trying to say is that when I look at this recurrence, I will be off by a factor of lambda, and I just have to adjust afterwards. Okay? Okay, so now I have a recurrence like this that I can simulate by building a tree. Are we good? So what does this mean? Well, if I look at a complete deregular tree, then my smaller trees are all the same, which means the activities that they implement are all the same, which brings me to the following univariate recurrence. Okay? And I can see, okay, so if I build my gadget as a complete DRE tree, does it give me anything? Well, hopefully it will converge somewhere to some fixed point. But there are some issues we need to talk about. First of all, I don't have the luxury of including an infinitely large tree, but that's a minor thing. Second thing is it even converging? And the second thing is, even if it is converging, I really wanted some desired activity lambda prime, and I'm getting some x star. Okay, so there are some problems. But let's take a little complex detour first. And what we are going to work with, if you look back at our recurrence, this is just a rational map, a polynomial divided by polynomial in lambda. So a little complex detour, when I have a recurrence that can be written as a rational map, okay, then I can talk about its fixed point, which is, well, I can do it anyway, but in this case I will be talking about rational map fixed points. So a fixed point when the value equals to the function value. But for rational maps, this is just a root of a polynomial, because I just take my QZ and multiply by Z star, and I want to get P. Okay? Okay. And then we have this concept of a multiplier at a fixed point, which is just the derivative at that fixed point. And we say that a fixed point is attracting if the norm of the multiplier is smaller than 1. It's repelling if it's bigger than 1, and neutral if it's equal to 1. And now we are going to use some theory of complex dynamics. So there is this notion of a Fatou set, which is intuitively points that start together, walk together. So what it means is that a point in the Fatou set Z0 for any leash length, right? So they're going to have a leash between them. for any leash length epsilon, there exists delta, such that if I start with somebody closer than delta to me, and then as I apply my map, the points will always stay within epsilon of each other. So they're going to be on an epsilon leash. Okay? It's a very interesting concept, a new thing to me before this work. But the thing that we are really interested in is the complement of the Fatou set, the so-called Julia set. And it, oh dear, okay, this was supposed to be higher up. The repelling fixed points are in the Julia set. Okay? Okay, so now the last bit of this is, so now it turns out there is a theorem in the theory of complex dynamics that tells us that if you take any point in the Julia set and some neighborhood around it, and then we apply our map to this neighborhood, we will cover the entire complex plane with the exception of something called exceptional set, but let's not worry about that. It doesn't really apply in our case. So the way to visualize this is the repelling, well, if my element in the Julia set is a repelling fixed point, you can imagine it as a fan. And then this neighborhood that you have, you can imagine it as a tomato that you're throwing at the fan. And if you do that, what happens? You have the whole room covered. Okay, so it's something like that. Okay, so now we're going to use this. How? Well, first of all, going back to the work of Patel and Regs, we can notice that for lambda inside the cardioid, there exists, for the univariate map that I put here for your convenience, there exists an attractive fixed point, a unique attractive fixed point. But for lambda outside of the cardioid, which is our case, all of the fixed points are repelling. Okay? So what happens next? Well, next, what do we want? We want to implement some target activity, the minus m, ideally, but we are given lambda somewhere in the complex plane. We know that the rational map is simulated by a D-regular tree, because that's how we got our recurrence for the map. And so the new game plan that we have is we're going to get close to a repelling fixed point, throwing the tomato at it, and then use the tomato Julia set theorem to cover the entire complex plane and get anywhere to our desired lambda prime. Okay, so now there are some issues to address here with the game plan. So what do we have now? So we know we have our rational map. We are outside of the cardioid and all fixed points are repelling. So we kind of want to get close to a repelling fixed point, but you know it's kind of hard because it's repelling. So what do we do? Well, let's go back to the multivariate map. In the multivariate map, we didn't connect trees that were all equal. We connected different trees that implemented different activities. Okay? Does that possibly help? Well, let's see. So this was the univariate map. This is the multivariate map that I'm including for your convenience. And what we are going to do, we are going to create our trees in a Fibonacci-like way. Okay? So namely, or if you want, you can look at it as constructing the x quantities in our multivariate map. Okay? So we start with some base cases. So our initial little trees are just little trees, or x is corresponding to 1. And what happens next? The next tree we are going to compute, or the next map, we are going to compute from the last d quantities we computed. Okay? So I tried to do a picture here. So this is when we are first merging all the little trees into one. So this is our d plus 1 case. Okay? And now we are going to take this tree that we have and 3 little ones, and it looks like this. And then we are going to take this tree, the previous tree, and 2 little ones, and it's going to look like this. You have no idea how difficult it was to draw. Okay, and then like this. Okay, I stopped here. So this is the Fibonacci tree-like construction. The question is it any good? Well, I guess the intuition for this comes from when we look at the multivariate map and we fix d minus one of the parameters, and then we have only one parameter to play with. Suddenly it becomes a contracting map in certain regions. So I think that would be my intuition for why this should work. But let's just go through a little calculation, and I'm going to show you that it actually has the effect of converging to the repulsive fixed point of the univariate map. So I'm using this multivariate map to get to the repulsive fixed point of the univariate map, and namely I'm going to get to the one with the smallest norm. We can show that all of the fixed points have different norms. Okay? So this is just a recap of the construction, and now let's see what happens. Let's look at the following polynomials. So I'm going to set my first d plus 1 polynomials to just 1, so a constant polynomial. But the next polynomial I'm going to take by taking the previous polynomial plus lambda times the dth polynomial from the end. So where am I going with this? Well, it turns out that if I build my polynomials this way, they represent independent set polynomials of the following graph. I take vertices from d plus 1 all the way to the k that I'm currently at. And now I claim that pk, the kth polynomial, is the independent set of this graph. And this is not difficult to see by induction, because when I add a new k plus first vertex, well, if it is in an independent set, it's going to have a contribution of lambda, and then it's going to kill all of its previous d neighbors. So then I will have to multiply by p of k minus d. On the other hand, if my new vertex is not in the independent set, then I'm free to take any independent sets from the previous k. So now, what's going on? Well, this graph has one other neat feature, namely it is claw-free. It doesn't contain this type of a claw graph as an induced subgraph. And Chudnovsky-Seymour showed that for claw-free graphs, the independent set polynomial has only real roots. Okay? So what I'm going to do now, I'm actually going to restrict ourselves to our lambda activity being given as a true complex number where it has some complex part. Okay? And in such cases, so I'm going to work on this. This is the harder case. So I'm going to assume that my lambda is somewhere in the complex plane, not on the real line. So then, these polynomials have only real roots, which means that for my lambda, this is a non-zero quantity, and I can divide by it. So what I can now do, I can set up a new variable, which is simply a ratio of these two polynomials, pk and pk plus 1, and I do a little calculation, and I actually notice that the yk recurrence is exactly equal to my multivariate recurrence. So from that it follows that my yk quantity is the same as xk, which means my xk's are just ratio of these two polynomials. It's a little bit like magic, and I don't really have any good intuition for why it works. But it does. Okay? So what happens next? Well, so now we are not really looking at polynomials. Let's look at it as a recurrence. And it's Fibonacci type-like recurrence. Okay? We are computing a new quantity from the previous quantities. And so we can apply the theory of linear recurrences, and we can just do the characteristic polynomial, look at its roots, and then the kth term, just like when we are doing a closed form expression for the Fibonacci number, it's a linear combination of the reciprocals of the roots of the characteristic polynomial. The same kind of thing happens here. And so what we get is that our quantity xk from our map, from our Fibonacci-like map, can be written as a ratio of these two polynomials, but each one has a closed form expression which is a function of the reciprocals of the roots. And so when we take the ratio, it is the smallest root that dominates as k goes to infinity. Okay? So the bottom line is we are actually converging with our Fibonacci-like construction to the repelling fixed point, because we have only repelling fixed points, of the smallest norm. Okay? So that was magic number 1. So let's see. So the game plan was we wanted to get close to a repelling fixed point, and then we wanted to use the Julia set theorem to get everywhere else. So what did we do? Well, we kind of did get close to the repelling fixed point with the smallest norm. That's a check mark, but we really wanted to get here. Okay, so this is some kind of a Fibonacci tree-like construction that gets me here. What happens next? Well, to be able to apply the Julia set theorem, I need the neighborhood. And I can now compute backwards from my lambda prime where in the neighborhood I should have originated from, so that my univariate map gets me to my lambda prime. Okay? But I got here, and I need to leave from here. So what next? Well, next, we are going to do 2 things. We are going to first generate a dense set of points within this neighborhood. And then we are going to boost the dense set to exponential precision, so that then we can leave and go to our lambda prime. Okay, so how do we create a dense set? Well, this is kind of switching gears. A lemma that has nothing to do with what was happening before, but will have something to do with it soon. If we have a complex, not real number z with norm smaller than 1, we claim that if you look at polynomials with coefficients that are non-negative integers, they cover the entire complex plane densely. And how does this work? It turns out that the case when z is of rational angle is the harder case, so that's the one that I'm going to draw here. So here is my z inside, so before it looked like this was my z. And I'm going to create polynomials with non-negative integer coefficients and evaluate them at z. Okay? So now, if my angle at z is rational, and I multiply z with itself, I kind of get all these points. These are all integer coefficient polynomials. And then, so that means that I can get arbitrarily close to 0 on any of the rays, and then I can use a coefficient in front of the corresponding z to the something term to get completely dense on the ray. So now I'm dense on the rays, and the last thing is, when I want to get a point somewhere else, I can write it as a convex combination of points on the rays, and I have to do the math with the integer coefficients, but it works out when I scale it up appropriately. So now, what do we have? We have all these polynomials that are creating a dense set in the complex plane. What we want to get epsilon covering over here. So we need to connect the polynomials to our trees. Somehow we need to be able to actually construct these polynomials. And so what we are going to do, we are going to first of all observe that we need only a finite number of polynomials to create an epsilon covering of our neighborhood of the fixed point. Epsilon covering means that any point in the neighborhood has to have somebody within distance epsilon in the covering. Okay? And so if I have this small set, just by packing argument, I need only a finite number of polynomials evaluated at some z to cover this. And I'm going to use multivariate trees to generate these polynomials. And namely, when I look at my multivariate map and evaluate it close to the fixed point, I can use a Taylor expansion. And my deviation original from the fixed point is going to be z times sum of the previous deviations. And so what this means is we can look at another recursive construction where from these deviations from the fixed point we are getting this one. So that brings us to the construction of all of these neighboring values around the fixed point. And now we claim that we can actually, for any polynomial, we can construct it using this kind of recursive construction, which, because of this connection, corresponds to just a tree. Okay? Okay, so now what's happening? The last step, and I know I'm out of time, so I'm going to end very soon. The last step is now we have the epsilon covering within the neighborhood of our fixed point. We now need to find, this is the point that would have eventually gotten me to lambda prime. I have covering that is epsilon covering, but I really want this point and to be close to it. So I need to boost my precision, and how am I going to do it? I'm going to find a contracting map on this neighborhood. And so if points were at distance something, now they're going to be a distance some L smaller than 1, so it's contracting with a factor of L. And so when this is my target, I can compute backwards where I should have been with this map, and I go backwards until I have a point and a desired precision in the neighborhood. And then I can just apply the map forwards, and because the precision always keeps getting smaller and smaller and smaller, I will get close to my target with exponential precision. That's roughly the intuition. There is some technicality that needs to be worked out, but there is a problem. The problem is that the map that I have could escape. So what we can do instead, we can create several contracting maps that have the effect of covering my neighborhood. So what this means is that any point in my neighborhood has a map that maps to it. And so that means that I always have an option of staying within this neighborhood, and then I can use the idea of doing the contracting maps to move me from an epsilon covering to the target point. And now, this is my last slide. It's a summary. So what happened? We start with our lambda. We build our Fibonacci trees. We get somewhere close to a repulsive fixed point. Then from that, we use our polynomials with integer coefficients to create a dense neighborhood, epsilon covering near the neighborhood of the fixed point. Then we use the contracting maps to get very close to the location that we really want to be in, so that then we can use another tree, the univariate map, which corresponds to a D-regular complete tree, to get close to our lambda prime target value. So putting these all together, we just get like a big tree, but not very big tree, big enough, and then we can plug it in to the reduction, and that will give us the number of independent sets. And so this is the picture, and well, we have some new results here, but the question is, what is the ultimate answer? Thank you.
Any questions?
Yes.
So do you think that this claw-freeness, so having a claw-free graph in this Fibonacci type recurrence proof, do you think that's crucial, or could you go about that?
Well, honestly, that construction that it actually works out to be the claw-free graph, to me it's a little bit like magic. So I'm going to look at Leslie if Leslie has some better intuition for why it actually should work, besides that it actually works out. So, no intuition, unfortunately. It's beautiful though.
Sorry, I mean, part of the claw-freeness was in the conclusion that then you have real roots.
Yes. Yes, so absolutely, absolutely.
So real roots gave you the density result. This was no real roots.
No, real roots gave me the convergence So real roots allowed me to express the activities that I'm building up with the Fibonacci construction. So I'm building these lopsided trees, right? And the real roots, I can express the activity that I'm building with these lopsided trees as a ratio of two polynomials. But it's meaningfully defined only if the denominator is non-zero. So that's where the real roots came in, because I was plugging in lambda that was a true complex value, not on the real line. But it's sort of like a
But also it was crucial for the density thing. When you rotate and take convex combination and you take non-negative combination, get closure gives you the entire plane. But that was, I think.
But those are the different polynomials.
But for that result, it was important that Z is not on a real line.
Yes, absolutely, absolutely.
That was,
absolutely.
I think, crucial thing. Yes.
Absolutely, absolutely. Though I don't personally see a connection between the claw-free real rootedness and
yes.
this.
You did not know that that number is not real, not to get the density.
Yes, 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 yes. So there is a kind of like a separate part of what do you do when you have a number and the negative real line. But I was focusing on the truly complex.
By the way, is there any other hardness result which uses so much of, let's say, chaos and complex numbers? I'm just curious. Is this the first one which uses all this kind of machinery?
I think so.
Huh? Yeah? This is like really cool. So it's another motivation where you need to study, you know, calculus and computer science departments. You know.
So you could imagine all kinds of constructions where you would give you the claw-freeness. So that's not so difficult to.
Yeah, but then can you then connect them to a tree construction?
Yeah, but you know, it won't be as. I mean, this will be one special.
Yeah.
But it seems like more applicable than just this almost like coincidental. I don't think it's that coincidental. It's this claw-freeness is a pretty robust property that you can realize.
Maybe I missed something. Why the final hardness is empty hardness, not sharp hardness? The final hardness is not.
Because we went for a problem of computing the number of independent sets in the given graph H. The very first reduction.
No, but it is
sharp.
It is number P.
It is number P.
Yes, no.
It also.
It's just because the slide said NP hardness.
I think she's referring to an older result.
Oh, yes. This is Sharpie hard also on the negative real line.
Okay.
Yes. It's a copy paste.
Okay.
Inside the cardioid, is there these techniques? Or what do you think?
We need a repulsive fixed point. So there are points of the Julia set inside the cardioid, I believe. But it's not a fixed point. So the question is, how do you get there? So
any more questions? So we break for lunch. Be back at 2:15, please. And thanks to Ivona.